Okay, thank you very much. I hope that also people from the online section are able to see the slides. So good morning also from my side. I will be really quick in order to start the meeting. So I'm Emilio Sanfilippo from the Laboratory for Applied Ontology at the National Research Council of Italy. Now we'll share today's section about the workshop itself, which is going to take place for today. And then for the next day, we're going to have meetings concerning IOF and OntoCommons. So if you don't know the workshop itself for me, I will just give you some general idea about what it is and where it comes from. So it is a flagship. It is a flagship workshop of the International Association for Ontology and its application, the EAOA, which is always a bit difficult to spell. It is organized, let's say, it's orchestrated by a steering committee within the association, which is called Industry and Startups Technical Committee. And the current member at the moment are Stefano Borgo from our lab, so the CNR in Italy, Michael Gruninger from the University of Toronto, and Amanza Wiesendahl from Credit Suisse. So today is the 12th edition, so it has been running already for a while. The purpose, as Heidi was mentioning, is that of putting people together from both industry and academia to have us talking about research challenges and application aspects concerning the use of ontologies in industry. Industry, I mean, it is in general understood in a very broad sense. So this year, I mean, we will listen to papers, so today mainly, which cover the following topics. So you will have aerospace, petroleum and multi-energy, material sciences, maintenance, manufacturing, design and functional modeling, requirement solicitation for ontology design, and meta models or foundational ontologies used for industry. So if you don't know something about these topics, you will learn hopefully what they are about. To tell something specifically about the 12th edition, so we will have the presentation of 7 full papers, 3 short papers, and 4 poster papers. Actually, the 4 poster papers will be presented on the 4th day, and one of the full paper will be presented, I think, on the 3rd day, because the authors could not be present today. We had 22 BC members, so again, many thanks to them for their really valuable work. The proceeding will be soon available on the CR workshop series within the association series. They are temporarily available at this website, which I just posted on AirMeet. And by the way, if you are the author of one of these papers, you should have got an email with the address. So you can go there and you can browse the papers. Okay, for the association in general, just to say something about it, I mean, it is a non-profit organization which is located in Bern, Switzerland, since 2016. It was founded in Italy in 2009. 2 major ambitions are those of scientific exchange and education and training. So the conference is mainly responsible for the organization of FOIS, which is the Formal Ontology in Information System, which is the main conference of the community. Then Joe
Resharing, yes.
I don't know whether they listened to my presentation. No. Okay, I'm sorry. Okay.
No worry. Okay, hopefully it works now. So, jumping back in, Siemens really has to offer a broad area of technology fields. And why am I emphasizing this here? I mean, this workshop and this community is about ontologies, formal ontologies specifically, which is a technology that keeps the promise of harmonizing and integrating data management across fields, across disciplines. And so what I want to say here, like this is the range that we have to cover. And later on, we have, I'm going to report on our endeavors to build up a company-wide semantic model repository. So this is the range that we have to cover. So that's to say that here. And when I say we, I'm referring to like the technology department of Siemens, where I'm working together with a bunch of other like scientists and semantic technology experts, maybe 5 to 10 people. We all like are trained in semantic technologies and ontologies, very much like people in this audience, I assume, and in this community. And the technique that we use to shoot at these problems is basically knowledge graphs and ontologies. So I just want to clarify a little bit of terminology here. So knowledge graph is really what we try to use as a tool to integrate all these various sources of data that we see, like ranging from relational databases to spreadsheets, all the things, and also like content-wise having engineering data, a bit of material, or plant setups and 3D models and all kind of things, but also time series data from operations. So anything. And what we try to do in projects is kind of to use knowledge graphs to integrate, like to put a kind of a data fabric across all these things to make them connected. And ontologies we see kind of as the orange bit. So knowledge graph is not the big thing that makes everything connected, and ontologies gives us the schema bits and pieces, like the knowledge and categories in which this data is being expressed in our knowledge graph. So that is kind of the how we see knowledge graphs and ontologies as part of the solution to this integrated data management. We have a couple of use cases, and I want to quickly report on some of them, on some of the projects before I go into this semantic model repository ideas. So typical use cases for knowledge graphs range from data quality on the one hand. So you want to, instead of having application-specific data models that are all like dispersed and siloed and have nothing to do with each other, you want to use like common schemas and semantic models to make everything aligned in modeling, so that gives your data a certain quality. And specifically modern AI applications, for example, based on machine learning, rely on good data, on high quality data. You use this data then for like giving access across sources. So with knowledge graphs and technologies like Sparkle and things, you want to do kind of federated querying across different sources that are otherwise like separate and dispersed. The next step would be to put in place digital companions that use this knowledge and run next to some other system, like an engineering system, and give the user advice of how to do the next step and things like that. It goes in the direction of recommendation, which is kind of a digital companion that proposes complete solutions to support people like engineers. And then also like constraints and planning stands for the idea that when you use knowledge graphs and ontologies, you represent knowledge, you can do more, you can put in place systems that really take their own decisions, do reasoning and planning, if you take it further, if you really formalize your knowledge in a strict way. And just to dip in some of these use cases, I start with the topic of digital twins, which is also kind of one of the newer buzzwords. So the idea of the digital twin is to take some physical thing like a machine here, for example, a gas turbine or whatever, could be it a plant or machinery, and to try to really capture the same thing virtually, like have all the information about it so that you can in the end even simulate physical processes on it, or do maintenance scenarios before you do it in the actual world. So that's the goal here. So, and what we did here, we applied this in the case of in the energy sector. So what do we find today in terms of digital twins? We already have kind of digital twins. Some people would say we have data like in databases and our sources, which are but siloed, so they can be accessed out there, but they are not connected. We do have also diagrams and documents describing a technical system like a turbine, but they are kind of, it's hard to access them, like they are made for humans to look at, not really for processing. And there's 3D models, so everything is there kind of, but it's just not connected. And what we want to do with knowledge graphs is here to take all these sources of information and read them into this data fabric, a digital twin data fabric that then connects the bits and pieces. And then the data stays where they are, like you wouldn't put a time series data into a knowledge graph or something like that, but you just link to this data and make things connected with that graph. And we did that, for example, for a case with these turbines, where we do turbine servicing. So Siemens builds gas turbines, and then later on, after delivery, does also after-sales services scenarios for that. And these people, the service departments, really benefit from having a good digital twin of a turbine that they can then use to simulate certain scenarios to improve their maintenance services for customers. So that's one scenario. Sorry, I'm not sure about the mic. Does it really work? I have the impression that sometimes it works. So, okay, so that's about digital twins. Then the next step, digital companions. I also want to give an example about a system that we use in a product. So what are digital companions, or the idea of digital companions is really to have a system that works next to another product or another system, giving you advices and recommendations using the knowledge of the domain. So there could be, or instances, there could be data companions that like do automated data structuring, or also validation of the data that you type into an engineering system, telling you whether your engineering solution that you're just designing is good, or if it violates certain constraints. That's things you can use knowledge graphs and constraint checking technology and things like that. Other things would use this knowledge to give like further recommendations. What is the next step to do? What, based on past history, based on other solutions that you derived your knowledge from, or also explainability. So once a system comes up with a decision, the knowledge graphs can be used to make transparent why the system actually took this decision. I'm going to give another example on that. It's a bit advanced anyway. And one particular example where we put a digital companion in place is for the TR portal, which stands for Totally Integrated Automation. That's a product that is used for factory automation. It's kind of the engineering solution for factory automation. It's a little bit like you might know, like integrated development environments, but just for factory automation hardware and software. So it's a development environment to make everything working in factories. And our digital companion sits on top of it, like using its data, reading its data, combining it with other data based on a knowledge graph, and then gives recommendations of what to do next in terms of various scenarios. So when an engineer is configuring like a hardware solution to make it work on the shop floor, so there are various questions like how to configure it exactly, or what to combine it with in terms of other components. Can I put another component like a network router or some other device on it, and how would it work? And this is where our assistant gives like suggestions for solutions that the engineer can just like then accept or decline. And how it works technically is that in the background we do have, you see this visualized in the middle part a little bit, a knowledge graph that captures all this engineering information. And then we use machine learning, actually we use graph neural networks to learn from past solutions what like other components are that would in principle fit in to serve a certain goal or not. And based on that, we give these recommendations. So also here, knowledge structures from knowledge graphs are utilized to realize such a companion for engineering systems. And as the last bit, this is not always working. As a last example of knowledge graph use cases, I'm going into this constraints and planning area where we utilize ontologies and their reasoning and inference capabilities to some degree. And here I want to like address the Industry 4.0 area. I guess most of you are probably familiar with it, or have even heard this idea. It's kind of a German coined term, but also you heard it in an international context. So the idea of Industry 4.0 is really to make your factories, your machines, your product kind of smart and autonomous. So currently, today, still most factories are really kind of everything is hardwired towards producing a certain product with a high throughput, very optimized, especially if you look at things like car industry and so on. It's not very flexible. So if you have a new product request, or if you want to change things and react flexibly upon market changes and so on, you have to reprogram your robots, you have to reconfigure things, you have to do a lot of engineering work. And the vision of Industry 4.0, or at least one part of it, is to flexibilize production systems, to be able to directly react on new product requests without or with a reduced amount of work in engineering, configuring, and programming. And one idea of how to achieve this is to equip your factory power bits and pieces with knowledge, like you equip the machines with knowledge about themselves and their environments, the products with knowledge about themselves and their environments, especially the machines with knowledge about their capabilities. So what is my robot able to do? So in order to program my robot for a specific task, the idea is to describe what it's basically able to do. And then whenever there comes a request for a new product to be handled by this robot, or a task to be performed on this robot, I can try to perform a kind of a matching of that task against the capabilities of the robot to decide, well, is that robot fit for that task, or should it go to some other robot or to some other machine? So that's basically the principle, and this is also where knowledge graphs and ontologies come into play and can help here. So as a means for capturing this knowledge of all the factory for things, and once you have that, you can apply reasoning and for matching. You can even do planning, and instead of like a person, a manufacturing planner, sitting down and really like devising a plan for manufacturing, the long-term vision is that this planning is done automatically, and like a new product request is really completely handled autonomously. The plan for production is being devised automatically, and all these kind of things. But that's of course the long-term vision. So we are far from that. But we dive into bits and pieces, and how we apply ontologies here is it's a little bit full, this slide, with details. But the gist is that on the one hand, we take product lifecycle management data, like bill of materials and also work plans, sometimes called bill of processes, and we annotate these things with what we sometimes call skills or capabilities. That's also something that's being, I think, researched in this community, how to describe machine skills capabilities. Interesting topic maybe for later discussion. And we use ontologies to describe things and to say like, oh, well, this operation here for this new product requires its assembling at this point and then adjusting at that point, maybe an assembling of a side part with the bottom part with in the range of certain parameters and in the range of certain values that the BOM gives us. And on the other hand, we also have our machines, and we use the same kind of ontologies to describe what they are able to do. And based on that, we can use our reasoning. This is one prototype that we currently built to perform this matching of tasks against machines. And in the background, there is ontologies, which you can see a little bit like catalogs of materials and what types of materials can be handled and which not. or catalogs of manufacturing methods. And there are certain norms that we apply and try to capture in ontologies to serve them. And it goes even further a bit. We can even do a kind of a explainable AI, also a very buzzwordy new topic here, because once you have an intelligent system that routes your task or that automatically allocates your tasks to some machine, as a manufacturing operator, you want to know, okay, why did the system decide to do it on that machine and not on the other? Or if it's not working, he wants to know, why is it not working and what's the reason? What can I do to remedy this? And here we can even utilize explanation techniques. You might know that in our ontologies there is something called justification. So you actually might know that from Protege, where you have this nice question mark button that you can use to explain an inference. And the same thing we do here. So whenever the manufacturing planner wants to know why a certain operation could not be, in this case, assigned to machine B, there was a mismatch, then the system would come up with a kind of a reasoning, would say something like, well, operation 2 is about assembling side parts. So assembly part in operation 2 is a side part, but side parts are casing parts, and machine B operates with a magnetic gripper, and magnetic gripper cannot handle casing parts because they're presumably made of plastic. So this kind of causal chains can be extracted out of the ontologies and knowledge graphs to be given to the user as an explanation of what's going on, which is also a sort of digital companion, it serves the user's understanding of things. Okay, so with this, I just wanted to give you a brief overview of use cases that we have realized. There are many more with knowledge graphs and ontologies. This is kind of a bottom-up approach. So here and there in this broad spectrum of industry fields that I showed, we realize solutions where knowledge graphs give us some benefit. But that's still far from having a company-wide harmonization of data models or information models, which is the next topic that I want to dive into a little bit. And this picture shows it we have this knowledge graph idea. The knowledge graph should lay across all the disciplines of our company and range from here, especially for technical machinery, from engineering over operations until maintenance, and covering everything, asset management systems that are used for maintenance, sensor actuators, time series data that are used in operations, and of course the engineering data systems and descriptions and bombs and whatnot. And all this should be integrated, and there's much more, as I said. And what we need for that is, of course, the thing in the middle, common semantic data models, which is the strong link to this workshop and to this community, I would say. So, and what we do here is, or we're at the beginning of that, I will say a little more about it, to set up a model repository, or semantic model repository, that is hopefully in the long run covering this broad spectrum. And we build what we call an ontology library later. So why are we doing that? The motivation is really, it's kind of clear. It's these four basic pillars of motivation. We want to reduce modeling efforts. So we want to avoid that people in the company rebuild their models from scratch again and again, because they have a lot of commonalities, even if the one automation solution has been done for train equipment and the other has been done for factory automation, there is still lots of commonalities. We want to speed up data integration. So when we have these models in place, we are in a much better position to actually populate them with data, produce ETL solutions that are harmonized via these models. Then also, across these life cycle phases, we want to integrate things. We want to reuse things, actually, to be able to reuse artifacts from the engineering phase in maintenance later, because they are related and they are important. And how people do this currently is that they look up in databases or spreadsheets or whatever, so they have to find things themselves. And with this integration, we also kind of integrate the cycle, the life cycle, so to say. yeah, so that's for the motivation, and what we build is this, what we call an ontology library. This is a sketch of how we envision this to look. I mean, this is not kind of readily available or anything like that. So it says content outlook. So it's really kind of that's where we want to go. And we have started, but we are rather at the beginning. What you see here is kind of a grid of models. So each like point here is standing for an ontology, maybe sometimes a set of ontologies or an area or a module in this library, and it's layered as all those model repositories that you might know, like they're always layered. In the middle, there is some very core things, and we do build on upper ontologies actually, on formal ontology. In this, currently, let me say, we have picked the ISO 15926 part 14 upper ontology, which is very much like, I would say, Dolce or BFO or other upper ontologies, very abstract categories, not really tied to any industry. We have actually evaluated, or we are doing this continuously. We look at all these upper ontologies and compare them and so on, and this is what we picked at that point. But it's not kind of carved in stone. We are like gathering our experience with it, and we see also the need to integrate in other things. But we need something to build up our core, and that's what we do. And we take other things into that core that are out there. For example, QUDT for capturing units and these kind of things, because like that's something you have everywhere, like in all the technical areas. Of course, you deal with units and the SI system and these kind of things, or provenance information. We use cost taxonomies. We use Web of Things and other things. So some really core semantic technology assets, I would say. The things that we also are like familiar with. Like, as I said, we are a bunch of technology experts in semantics, so we really have a background in REF, OWL, reasoning, and all these kind of things. We do consider other things also, but I would say like this is our standard solution for knowledge graphs. But there is also other things like property graphs and things like that. We also do consider this, because for some of the use cases, these other technologies are just more suitable, and we don't want to miss out any of this, but that is the core. And then outside, in the outer layers of such a repository, you would find like industry-specific models. Not really application models; they are even further on the outside, I would say. But things that repeat across projects and use cases, like anything about building, energy, rail production, to name just a few. That's also just a sketch and a start, and there's going to be more. And this is kind of the layered schema that we want to realize for this. Maybe one thing to be said, that we are building around these most inner things that we know from semantic web community. We are building other core elements, like topics such as geolocations or logistics or maintenance and other stuff. That still are in the core, that apply to all these industries for the matter of, for the purpose of reuse. Let me see. I think I've covered all this. Maybe let me also just say that we use semantic technology also as a technology. Like we use RDF triple stores and have built up an infrastructure based on triple store solutions together with ETL frameworks to load data and all these kind of things. We use OWL ontologies, RDFS ontologies, if you will, so all these kind of things we use as a technological basis. Also, what is important to mention, also to understand what I'm going to say about lessons learned later, is that our small group cannot do this for the whole company clearly. So we are not enough people. So what we need to realize such a vision is to integrate and to involve people from our business units. Like we cannot sit down and model all the ontologies for this whole spectrum. So we really need to involve like engineers, end user kind of people, developers that are like facilitated in their industrial fields, and we together with them we need to enable them actually to contribute to these models. This is also our concept of modularization. It's not just technically that these things are technical modules that import each other and things like that. It's also like we need people who can get assigned like responsibility. So somebody who is responsible for building up the power meter parrot or something, yeah, and then they involve other people, and then it's structural, and we need processes to set things up and to communicate. So this is also part. It's not only technical. A lot. This is about involving people and setting up processes to develop models. And yes, maybe a last bit of a little bit of a glimpse of how we set up these processes. On the one hand, we put together an ontology guideline document, something that people in this community are probably very familiar with, like the typical guidelines of how to model ontologies, you know, like the naming conventions that are out there, and how to deal with classes, and when to use classes, and when to use these kind of things. We put them into a guideline document because the developers that we want to involve have never heard about these things, so that's very helpful for them, but also for us, because there's still a lot of design decisions that you can take in ontology modeling. So there's no right or wrong. You can do it this way and that way. And guidelines help this harmonization, and we need to do more about that still. We do have like tooling to support this, like a model documentation pipeline. So there's a Git repository where we maintain all these ontologies, and we do things like automated checking of content. So whenever somebody contributes a model, there's a bunch of shackle constraints that is run in the background to check if they did things right according to these guidelines, but still also very at the beginning. And there is automated documentation generated. That's very important because people need to look at things. So if you send them a turtle file, that's difficult. So, but if you have a web-based or generated documentation, that's better. We are building this core model still, so that's what we mainly do within our expertise area. And there's still kind of questions as how to use our ontologies and things, so I will get to that later. But we also connect to the external world, so to say. So on the one hand, we participate with external partners, also with universities, for example. Here we are associated partners to Commons. So we try to get also connections to the outside world and to get solutions to bits and pieces of such a model repository. Maybe there's models that we can take in. There is standards out there that's very important that we need to connect. There's a lot of industrial standards that are being used, just to name a few. For example, there's this DIN 8580 norm that sets a catalog of manufacturing methods into place, or there is E-class that describes a catalog of all product parts and things like that. So this is very important. If we want to make this fly, we need to somehow connect this to existing things. And so we involve in these kind of activities also. As the last bit, and I think I need to go through this a little bit quick. Let me try. I want to very completely get a little bit more technical as to our experience in applying ontologies and formal ontology in particular. So I put together 4 categories of lessons learned. It's not really a lesson you learned yet. We are still in the way and in the process of learning this lesson, so it's more of an insight, but still worth reporting, I think. So on the one hand, a lesson about applying ontologies in general, which by which I mean to use ontology as a generic conceptual model across applications, so that not every developer builds their own application models, which is kind of still common today, but to use them for integration. So the promise here is that ontologies will be reused across applications to integrate that data. Yeah, that's what we used it for. But is this still like happening? And what about the reuse really? Are they really reused? And what we find is that typical developers, they are not in this mindset of reusing models. Typically, they start modeling from scratch, and then they build their model and put it on paper. Then they program their application from it, and they put the paper into the shelf. So they're not using it as a computational artifact. Clearly, ontologies should change, but it's hard to get like these developers to do that because there is no processes for this established like out there in the companies or in our business units. So it's just like the classical software development is still like in the minds of people, I would say. What we try to do to remedy this a little bit is we want to set up this process, of course, but it takes time. And we want to provide good documentation. That's a good start, I think. If we compare this to software libraries, where I think reuse works quite well, so yeah, programming of code is being reused in form of software libraries. Why does it work there? Why does it not work so well for ontologies? Maybe one idea is to, there you have good documentation, you have API documentation that clearly tells you how to use the thing. And in ontologies, it's often not so clear of how to use that thing. Yeah. So we started with this kind of, you might know Widoko, we use that as a tool in our pipeline to generate something that looks like an API specification that helps the developer to better work with it. Sometimes if people say, okay, no, they really do not include the technology like RDF, OWL and so on into their stack, it also helps to just hand out a UML diagram of the model, because some design decisions are already taken in there. And if they take this, it's better than starting from scratch, so to say, when we later on in a second iteration want to integrate further. Another kind of a lesson is about semantic web technology, so the technology underneath, by which I mean to utilize RDF, OWL, and also Sparkle, Shekel, and all these related languages to build ontologies. So the promise here is that these technologies are provide ready-to-use tools for building ontologies. But is that really so? I mean, of course, it is. We are all using it. It's great actually to have this standardized. If there weren't these standards and the tools and the communities, it wouldn't work in the first place. But there is still some issues. For example, with that semantic technology stack, there is still incompatibilities, and these languages don't form one coherent like framework really, because bits and pieces are kind of, it's not really layered on top of each other. Sometimes it is a little bit on the side and so on. And we all know the semantic differences of OWL with a first order logic based framework versus RDFS, where you have meta modeling and can kind of build kind of higher order structures. And once you do that, you stop to be compatible to OWL and things like that. And also Shekel is really for validating constraints. It's not well integrated with the reasoning features, especially of OWL, not at all, so to say. So it's not that everything works tightly together. It's just it works together, but there is still bits and pieces of incompatibilities. And the staff is of course not trained. So like it's still kind of an exotic technology, I would say, in companies. Everybody is used to software development technology. Everyone's using databases and JSON and XML, of course, but REF is still kind of exotic. It gets better. And also the staff is not trained necessarily in declarative methods. I mean, computer scientists nowadays are typically still trained or mostly trained in imperative languages, yeah, clearly. So it's kind of new to them. And this is maybe a reason why RDF OWL is often just too complicated. So sometimes developers say, okay, like hand it over. It's just to get another XML format. I'll check it out and in 3 days I'll know it. But of course that won't happen. And that's a barrier, clearly. And also the situation of modeling tools and editors is not really satisfactory. So most of the people are using Protege, but that's an expert tool, and also other solutions are really expert tools. There's not really like end user tools. I mean, there is companies who go in that direction, and we are also in contact with them here and there and trying out their tools and re-evaluating the tool situation. But currently, I would say it's not really satisfactory, especially if you want to address classical software developers and end user kind of people. Another lesson would address the topic of ontology modeling techniques. By this, I mean use the language contracts of RDF and OWL according to patterns and the typical conventions that are there. And this community is very much about patterns and these kind of things. So I assume you know what I'm talking about. And the promise here is that when I do this, when I apply the patterns and when I model according to the rules, so to say, this will give me ontologies that are coherent. Like if everybody's doing like this, everything will fit together. But the question is, does it really? And to what extent does it? And there is still kind of a lot of decisions to be taken. For example, when do you use RDF type to instantiate things? So that goes back to the question of when to use classes versus instances. And on this little like visualization, which is actually taken from a case where we apply ISO 15926, which has a distinction between functional objects and physical objects. So on the physical object side, you see a typical subclassing of device into motor control units, motors, and other things. So that's how you would do it, like in the OWL world. But often then practitioners come and say, oh, well, I want to attach really like attributes to these things, and not in terms of axioms saying every motor has this and that or so. I really want to attach like by means of simple triples attributes to motors and control units and so on. And this is why often in practical models you find these instantiated, not being classes, but being instances of something. And then you can do it like the one use case, for the one use case, the one way is better, for the other use case, the other way is better, and then you cannot easily decide in these upper models, would you do it like this or like that? So that's a little bit of a difficulty, like where to place these design decisions. Do you want to place them in the upper models, or do you push them down in the use case specific models? And then properties is the same. Do I use OWL data type properties? But then I cannot do more complicated things like using units and measures, yeah, or not so easily, I would say. Like if I just have them plain, or do I kind of reify them in terms of making OWL classes of them, which carry their values in them and so on? When to do what? And do I use these kind of data properties to capture attributes at all, or is that use case specific? Our experience is that each use case has their own large list of attributes that are really interesting. So do we put them into the domain model about manufacturing, or rather say, oh, well, no, that's not what we do. So, and where do we draw the line? And that's a bit of also decisions. So our current solution is really to stick to the basics, rather have simple class realizations of ontologies in these common models, and not be too specific about it, so to say. And the last lesson that I want to report is actually the most important one for this community and for this topic. It's about applying formal ontology, like the topic of the whole workshop. And by this I mean use abstract upper level categories to align domain models, and you all are familiar with this, I assume. And the promise here is that these ontological categories support harmonization of data management. That's what we want from them. They are so abstract and general that they are not tied to a specific industry. They can cope with everything and hopefully then integrate everything. But also here, I mean, that's a good idea and a good thing, and we are using it, but there's still problems also with that. I mean, the acceptance for very abstract categories is one thing. If you go to these practitioners and software developers, with something like per durian or current, that's always kind of difficult. You have to do a lot of explanation and things. So the question is, who should see that then? Yeah. But as I said before, we, the semantic technology experts, we are familiar with this. We can cope with it. We can use it and utilize it and make value out of it. But in order for the thing to fly, we need, as I said, to involve people from the business unit, and this is why we do need to make them familiar with these concepts also. So that's this topic of understanding that's sometimes a bit strange. I mean, then yeah, it's a bit funny because it's kind of philosophical, and that's what they say. They look at us and say, oh, well, this bunch of crazy scientists who play Aristotle categorizing the world or something. So, but of course, we want to give them the value out of it. But this discussion is difficult, huh? So it's not easy to accept. And then there is also a bit more technically the issue of sometimes you have an overcomplication of application models due to what I called here unnecessary ontological distinction. Unnecessary in the sense that a certain use case might not need or require the distinction between the functional view of a plant versus the physical instantiation. I mean, that's very helpful, and I think we see also in the later sessions applications of that, even more aspects of separation. But some use cases are so simple that this just overcomplicates their model. And when do you apply these patterns? And if your uppermost models require everybody to make these distinctions, and these upper models are always about ontological distinctions between the person and its role, because between functional and physical, between anything. Yeah, that's their job, so to say. But when to apply what, and what to require and what not, that's a bit difficult if you want to cover this range of users, like from semantic technology experts to the practitioner and software developers and end user type people. Okay, so that was my report on the lessons. As a conclusion, I would say we are using ontologies, knowledge graphs. That's a very promising tool. That's what we are in that. We are using it across a lot of disciplines. So really we have to cover a big spectrum. It starts to work, but as I try to make clear, there is still a lot of barriers and challenges for their utilization. And it's not only of a technical nature. Many of these challenges are really of a process and involving people nature, especially in large companies. Okay, so thank you very much for your attention. And if you're around the next days, I'm also, and I'm glad to have a chat on these topics with you.
Thank you very much, Stefan. Are there any questions from the audience before we move to? Yeah, there is an online question, but from the audience, is there any question? Otherwise, yes, we can go to the.
There is the online one.
Yeah. We'll get the online question too.
Okay. Hello. So thanks, Stefan, for the very interesting presentation. So my name is Ginger from EPFL. So I have maybe two questions related to the presentation. The first one is when you develop this platform based on the knowledge-graph model. So for example, across the whole domain, we have heterogeneous data like a SysML, UML, or 3D model you mentioned, or some requirement items. So my question is that do we need, so based on your current experiments, do we need to capture all this information from this domain data? Or, yeah, this is the first question. I mean, how to decide the detail, how much information we need to capture from this heterogeneous data? The second one is that there already have other RDF specification like OSLC, Open Service Lab Circle collaboration, just about the data interoperability. So my question is that currently, based on your approach, based on your current idea, so the knowledge-graph model can replace such standardizations in the future to support the data interoperability. Thank you.
Okay, let me try to. The first question was to decide which information to integrate. That's often given by the use cases. It's saying like we need this and that. That's already a selection of the things out there. So you need to combine like engineering data records together with operations data if you want to do proper maintenance, because you do need this information together in place. As for integration, it's a question of what you mean by capture. We don't necessarily load these things into RDF representations always. Sometimes we stop at a high abstraction and point into data sources. So that's a way how to deal with that. Actually, how to avoid try to integrate the whole world, which will clearly not happen. So I think that's. But the decisions are kind of individual for per domain, per use case, per project in a sense. Often, and I don't know the other initiative that you were mentioning, but I think that in particular, knowledge graphs are just a good technology candidate. I don't know what they use on a technical basis, but for integrating all this kind of different information, you need kind of this semantification of the representation in a sense. So I think that a step like the W3C languages are also well established and form a good candidate. I'm glad to hear like alternatives. If something else works better, let me know. But that's what we currently see it for.
Okay, thank you.
So maybe we can get a question from the web. So there is Zaid Antonietta asking, what upper level ontology does Siemens consider for its core in the main specific model? It's a known upper level ontology. I think that you already discussed about this.
Yeah, I mentioned briefly on the slide. Maybe you haven't seen it. It was a little bit small on the slide. We are looking at the upper ontologies out there. We started our work currently with the ISO 5926 Part 14 upper ontology, which is very similar, and I think inspired by BFO and also with others. But we still observe the world of upper level ontologies. Actually, we looked at their approach called GIST, which is also interesting because it gives you more concrete categories. So the acceptance by practitioners and developers is better, so to say. It kind of lacks this very upper notions. So integrating this with one of the other things would probably be a good idea. But like we are observing continuously, so to say, the landscape of ontologies, and whenever something is promising, we want to try it out and know more about it.
Okay, thank you. Maybe we get one at most two questions from the audience. Yeah.
Okay, thanks for your impressive presentation. I have one question because you mentioned we need to link the different stage of the life cycle and we need to reuse a lot of things. So can you give us a case or a small example like how you did it in operation and maintenance?
In operation, and what was the last part?
Operation and maintenance. Maintenance.
Ah, okay. Yeah, I see. Well, this is a good example of linking two things, because if you want to do maintenance, you need to know what has happened. Like, I don't know, the system is being broken, or a machine in a factory is being broken, and you need to fix it. But in order to figure out what the actual problem is, you need to look into the operations part. You need to look into the log of events of the system or something like that. So, and at the same time, you need like the engineering bits and pieces of data that you would consider in the maintenance phase also as kind of assets that you have in your factory, and you need to kind of link these two worlds. You need to ask a query saying, give me all the sensors that are related to that event that happened in the time where the problem occurred, or something like that. These kind of cross-querying scenarios is what we do with knowledge clustering.
Do we need to ask from the design engineer, or we ask the operational engineer? So because the life cycle is from the design to operation, so it looks like we need to have a lot of questions.
Sure, it's a challenge to integrate all these phases, and we have different sources. Like design engineers are a source for this knowledge, and we want to capture the knowledge that they have in mind and in their heads. Also for operation and maintenance, it's a challenge to capture all these things, but that's what we have to do.
Okay, maybe we get a question from the system. So Matthias is asking, does Siemens have a position such as knowledge scientist, acting as bridge translator between developers, business people, semantic experts?
I would say, well, but it's not kind of an official position. So say it's the role in which we are acting. We are mostly kind of scientists with backgrounds in some of the scientific communities. Here, like my colleagues that work in the Semantic Web community, there is other experts for everything, like machine learning, NLP, which we have in technology, and we just try to combine our knowledge and experience to solve these kind of problems. And when you work as a technician with ontologies, I think you do have to address that aspect. The knowledge engineer has to work in cooperation with the domain experts somehow. I think that's always this kind of pattern of cooperation. Yeah, and here we are on the one hand the knowledge engineers, but also in our cooperation with business units, we build up knowledge about the domains a little bit. So we are a mediator in the sense. Yeah.
Okay, I think that fortunately we have to move to the next section. So thank you again very much, Stefan. It was a really, really interesting talk. I mean, we are there during the coffee break, and maybe we'll continue the discussion. So let's start. The first speaker of the workshop with Francesco Compagni, I think. And Argo, can you please, maybe does anyone help us with the system?